these, and we have we're gonna have 12 of them in all. There's gonna be like kind of A and B for both parts. So we really have like 24 of these. So it might seem complicated at first until you realize, hold up, you've seen all these identities before. But yeah, so we can't prove them all, but I was going to state them right now for the record. And so set identities. And these are just set operations that turn out to be equal to each other, or combination set operations that turn out to be equal to each other. So number one, we have what's called the commutative laws. And that goes like this. That says A union B is equal to B union A. And then we also have A intersect B is equal to B intersect A. This one's kind of nice and obvious, right? I hope, right? It's like if you take everything, if you take the combination, if you take the set A and B put together, it doesn't matter if you do the set B and A put together. It's just everything and everything, but just everything. If you do A intersect B versus B intersect A, like the shared elements of A and B is the same thing as the shared elements of B and A. So it doesn't really matter there at all. That's commutative law. Stop me here for a question, Herman. But two, we have the associative law. The associative law says that A union B union C equals A union B union C. And we also have that A intersect B intersect C is equal to A intersect B intersect C. I'm gonna like a nice divider so we know when one ends. So the point being, this is kind of clear once again, I think. It's just that the order in which you do these unions doesn't matter. If you do A union B first, or you do B union C first, A union B union C, it's still just all these sets put together. It doesn't matter like the order in which you put them together. And same thing here. This is just the middle of the Venn diagram of all these sets. This is just all the elements that A, B, and C share. So it doesn't matter if you look at all the ones for A and B, and then do C, all the ones for A, B, and C, and then do B, whatever. I think this makes sense. And I guess one way you can see it, if you want to do a Venn diagram real quick, if you had A here, and you had B here, and you have C here, right? A intersect B, that's going to be this bit, or that's going to be this bit right here. But then if you intersect that with C, oh, well, we just get this part of this is in here. This is going to be the middle, the very middle part. But if we do B intersect C, then we get this side. We get this like weird fat banana thing. But then if we intersect it with A, well, we just take this middle part again. So it doesn't matter. Here's where it starts to get interesting. 3 is the distributive law. And what the distributive law says is that says that A intersect B union C. So now we're kind of mixing operations. Here we're all unions, all intersections. Here we're mixing up that. So A intersect B union C, that's going to equal the set that is A intersect B union A intersect C. So you literally distribute this A intersect to the B and the C here, to the B union C, which is interesting. And then same thing with if we have the other way around. So we have A union B intersect C. That's going to equal A union B intersect A union C. Once again, now we're distributing the A union to the B intersect C. And Herman, what's this remind you of so far? All these laws, all these identities.
All the kind of like all the same ones we been going over, especially like the beginning with the De Morgan's laws and stuff like that.
Yeah,
same
it's
associated communities.
absolutely basically exactly the same as all the operations we had or all the logical operations we had. Because underneath the hood, right? Like if we look at this right here, for example, let's do a really easy one. Underneath the hood, A union B, this is all X in a universal set such that X is in A or X is in B, right? But based on our logical laws, X and A or X and B, we know that's the same thing because the commutative law for the OR operator, or this is the same thing as X is in B or X is in A. But then by definition, this equals B union A. So literally what's happening in all of these laws basically is we're using the logical identities on this part of the sets. Like if we have A intersect B union C, well, that's going to equal A intersect B union C. That's all X and U such that X is in B or X is in C. Like that. But then if we intersect that with A, we get that, well, this is going to be by definition all X and U such that X is in A and X is in this set B union C. But if you're in the set B union C, that means if X is in the set B union C, that means X is in B or X is in C. This is all X and U such that X is in A. And to be in B union C, we need X and B or X and C. So we get X and B or X and C. And once we have it, what happened? Okay. Once we have this right here, well, once again, our logical operation identities are hiding here. Like this, we can distribute that and. This becomes X and U such that X is in A and X is in B, or X is in A and X is in C. What's that become? Well, if you have an or here, right, like after the bar in this set notation, well, that means this is going to be all X and U such that X is in here or here. This is going to be all X and U such that X is in A and X is in B, union X is in U such that X is in A and X is in C. But then each of these, X and U to the X is in A and X is in B, well, that's just the shared elements of A and B. So this is just A intersect B, union. This is X is in U to the X is in A and X is in C, so shared elements of A and C, A intersect C. So you see that hidden in all of these kind of proofs, we're gonna have the logical identity, the analogous logical operation proof within it, and then everything else just kind of builds to and from it. So that's why that we're gonna have this like really nice analogy between set identities and between logical identities, because the logical identities are literally embedded into the set identities, which is interesting. Does that kind of make sense, Herman?
Yeah, no, that makes 100% sense.
Oh, I like that. Good. Cool. So let's keep moving then.
If we were ever kind of lost on these operations, could we always draw that out logically like we just did and see what the operations were?
No reason not to, yeah, for sure. But I don't think you'd be lost, because once you do a couple examples of these, it's going to become like second nature, just like I did with logical operations, I think, where you're like, oh, clearly I'm going to distribute the negative and all that. Anyway, so 4, we have what's called the identity laws. These are really simple. These are just saying that A union the empty set is just A, because we're not adding anything, right? We're union empty set, there's nothing in the empty set. And we also have that A intersect the universal set just equals A. Oh, by the way, let's say let U be universal set and A, B, and C sets in universal U. There we go. So yeah. So if we intersect A with the universal set, if you think about what that is, well, that's going to be everything, the shared elements of the universal set in A. But A is just literally inside the universal set. So everything in A is in the universal set. And so the shared elements of A in the universal set is just all of A. So, yeah, so that's why it just equals A. And nothing outside of A could be an A intersect U because, well, it wouldn't be an A, it wouldn't be a shared element. So I think that makes sense. Just think of the rising sun. So that's 4. 5, we have complement laws. And these are just like the negation laws. And so what this says is that A union AC, we did this one last time, A union AC just equals U. Because once again, if you have everything that's in A, and you combine them with everything that's not in A, well, that's just everything in the universe. Oh, and we have A intersect A complement equals the empty set. And that should make sense because literally A complement's defined to be everything not in A. So A and A complement cannot share any elements. Because if it did, that would mean there's some element in A that's also not in A, which makes no sense. Yeah, you can either be in A or you're not in A. That comes down to like why sets are these rigorously defined, or why sets are these things. It's just you're either in or out. Comes down to that. Next, we have the double complement law. And this one is just like the double negation law. Really nice and simple. Do not forget it. But everyone forgets the double negation law because it's so easy. Do not forget this. So this just says that A complement is just A. Which makes sense. Again, if we draw it out, right, if A is this, A complement is everything not in A. And the complement of that, well, that's just what's left over, which is A itself again. Number 7, we have idempotent laws. And these say that A union A just equals A. And we also have that A intersect A just equals A. Obvious, right? Adding, like if you're adding A to itself, you don't gain anything. If you're taking the shared elements of A and A, that's just all of A, right? Yeah. Should be called the obvious laws, second idempotent. But anyway, we have that, and then we have the universal bound laws. These are interesting. We had very equivalent things in logical identities. So this is just saying that A union the universal set is just the universal set. Basically just saying that you can't get bigger than the universal set because the universal set's kind of what you consider the universe to be. So since A is inside U, if you add A to U, we're not really adding anything at all, right? It's like I said, it's like if I said, let's consider all of the North American countries, Union Canada. Well, Canada's already in the universal, it's already in North American countries, so you don't gain anything. And then the other way around is that A intersect the empty set is always going to be the empty set. Because A and the empty set are the shared elements. A intersect the empty set are the shared elements between A and the empty set, but there are no elements in the empty set. So there's nothing to share. So it's just the empty set. Then 9, we have De Morgan's laws, finally. And they work the exact same way. It's going to turn out that A union B complement equals A complement intersect B complement. And then we're also going to have that A intersect B complement that's just going to be A complement union B complement. Just like that. We're actually going to prove that. It's going to be one of the few things we're going to actually prove this class. And then we're going to have 10. Well, actually, yeah. So 10 is going to be, this is called the absorption laws. And they go like this. Now these are kind of the interesting ones that you hardly ever use, but I just want to show you guys. A union A intersect B. Well, if we look at A union A intersect B, we don't even really need a different law for this because this really comes down to the distributive law. But a distributive law is going to be A union A intersect A union B. But A union A intersect A union B. Well, A union A by our, where is that? By our idempotent laws, A union A, that's just A, intersect A union B. But then A intersect, well, actually, let's just forget all this. The point of this is that we should notice that A intersect B has to be a subset of A, right? So since A intersect B has to be a subset of A because it's shared elements of A and B, so all we can do is, like it has to be like the middle of that Venn diagram. So like the best it can be is A. And so A union this subset of A, well, that's just A. Right? Because I mean, here's what we have basically. Like if you have A union any subset of A, right? Well, that's just going to be A because you don't gain anything. Because A intersect B can't give you everything. It can't give you anything that's not already in A. And then we also have here A intersect A union B. This just equals A. And this was a little harder to see, but the idea is, actually this one's probably easier to use like distributive law on. This says you get A intersect A union A intersect B. A intersect A, that's just A union A intersect B. Oh, that's exactly what we had up here. So really the same thing. Anyway, these just both equal A. This is kind of interesting. 11, we have complement of U and the empty set. And so U complement, if you take everything that's not in the universe, well, like U complement, remember everything we're doing is within the context of our universe. So the universe is the only things that we're considered to matter, the only things we consider to exist. And so if we take everything not in U, but in the context of U, that's just the empty set. And then if we take the empty set complement, so everything that's not in the empty set, well, that's just everything in our universe. Because nothing's in the empty set. So everything is in empty set complement. I think that makes sense. I mean, this is just like how the opposite of true is false, how the opposite of false is true. It's very interesting. Anyway, very last but not least, you have 12. I like this one a lot, actually. And this is the set difference laws. And that is that A minus B equals A intersect B complement. That's really nice. Because A minus B, this is like everything in A that's not in B. But that's kind of like the shared elements between A and not B. So A intersect not B. Any questions with these laws? There's a lot of them.